Now we're going to talk about the three-dimensional system of equations. So we have three linear equations with three unknowns, x, y, and z. So the goal, just like in the two-dimensional case, is to find values for x, y, and z that you can plug in to each of these three equations to get a true statement. So a solution is a triple of numbers that you plug in for x, y, and z respectively to make the system true. So each of the three equations must be true. So the two-dimensional system represented lines, so each equation, the graph was a line. So if a pair of points would satisfy each of the two equations in the two-dimensional case, you're looking at an intersection of lines. In this case, each equation represents a plane. And when you have an intersection of three planes, it could be like two walls and a floor intersecting, so they could intersect at one point, or they could intersect at no points if two of the planes are parallel, or it could intersect at infinitely many points if at least two of the planes coincide. And if you want to solve this graphically, it's very difficult now. In addition to the difficulty of graphical approaches, it's even more difficult because now we're talking about 3 dimensions. So we will use the algebraic method. There were two in the two-dimensional case, the addition method and the substitution method. In theory, we could use either method or an analogous approach to the three-dimensional case, but we will use the addition or the elimination method. So that was the second method. So let us look at the example here. So this is just a specific example of three equations with three unknowns. And the first step is to choose a pivot. Ideally, you would choose a pivot, which is circled here in pink, that has a coefficient of 1 or -1, because that will be easier to do the following steps. If it doesn't happen, it can still be done. It's just a little bit messier. Okay, so the first step is just to choose what you're going to do. Now the idea here is to use that first equation and eliminate the pivot variable. So here in this case I'm choosing the pivot to be x. So the pivot variable is the x variable, and I'm going to use the first equation to eliminate, through addition, the x variable and the other two equations in turn. So this is a two-step process in this case where we have three equations. If you're lucky, one of the coefficients would be 0 and then you'll have to do it once, but that's not the case here. So the idea is to multiply by appropriate numbers in order to eliminate the pivot variable in the other two equations. So in this case, for instance, to eliminate the x in the second equation, we can add a and b. So that is x plus 2y minus z equals -3, plus the second equation. So already these cancel out. We're going to call this equation D. Just going to go down the alphabet. Hopefully we won't run out of letters. I don't think we can possibly do that in this three-dimensional case. Okay, what do we do to eliminate the 2x? We need to multiply the first equation by -2 in order to get the opposite of the 2x, so that when we add we get 0. -2x minus 4y plus 2z is equal to 6, and c is 2x minus y minus z equals 1, and we add, we get negative 5y plus z equals 7. I'm going to call that equation E. So to find y and z, we're going to use equations C and E. Now, just to see this as something familiar, I'm going to write the system down. So this is just a system of two equations with two unknowns, which is what we did in the last video. So this is familiar. So to eliminate the z, we notice here that the equation 1 we could factor or divide by 3 and still get integer coefficients. So let's do that in this case. I think that would be easier. You don't want to create fractions if you can help it. But in this case we don't, and we can simplify that equation and keep the numbers smaller. So in this case we can add. And that gives us negative 4y equals 4. That y equals negative 1. We could plug that into the first equation to find z, or we could use elimination again, and for the sake of practice with elimination, I'm going to multiply the first equation by 5, and we get the system. Gives us negative 4, z equals negative 8. We're going to use the information we found about z and y to find x. So we know from the first equation A, x plus 2y minus z. We should check that as an answer. So how do we do that? We plug it in each of the three equations in turn. So 1 plus negative 2 is negative 1, minus 2 is negative 3. Negative 1 minus 1 is negative 2. Minus 4 is negative 6. 2 plus 1 is 3. Minus 2 is 1. So this satisfies each of the three original equations and therefore is a solution. It's so easy to make mistakes, so do check your answer. And then try these three problems. The first problem is very similar to what we just did. The second and the third one have a twist, so you definitely want to try those problems out.